Hi, in this video we are going to discuss interference and system capacity. So what do you mean by interference? It is a major limiting factor that will affect the performance of a cellular radio systems, and it will create the bottleneck in increasing capacity, because capacity is the one important factor while designing a cellular system. As number of mobile users are increasing day by day, we have to accommodate all the users within the available spectrum. That is one of the important bottleneck in designing a cellular architecture. And there are two channels, one is a voice channel and another one is a control channel. So interference in voice channel create a crosstalk, whereas interference in a control channel create a missed or blocked calls. Missed calls means call will be lost. A blocked calls also resembles the same. And in urban areas usually we have more interference because of there are a lot of factors, that is a greater RF radio frequency noise floor and more number of mobiles are available. And the main sources of the interference is another mobile in the same call. Then there may be interference created between these two mobiles. And sometimes a call is in progress in the neighboring cell instead of the current cell. That will also create a interference. And other base stations operating in the same frequency band will also create a type of interference. And the non-cellular system leakages, for example your FM radio and TV channels will leak some kind of energy into the cellular frequency bands. So these are the main sources of interference. And there are possibility of two types of a cellular interference. One is called as a co-channel interference and another one is called as a adjacent channel interference. First we discuss what is co-channel interference and how to calculate the system capacity. And we know the concept of frequency reusing. That is, there are several cells that uses the same set of frequency. Only the consideration here is we have to keep the interference to the minimum level. So the cells that uses the same set of frequencies are called as the co-channels cells. The interference between the signals from these cells are called as a co-channel interference, shortly known to be CCI. And we cannot simply control this co-channel interference by increasing a radio frequency power. Rather, what we are doing is that will increase the co-channel interference. So if you want to reduce the co-channel interference, this co-channel must be separated by a minimum distance. That is the only way to reduce the power level. So when the size of the cell is approximately same, then co-channel interference is independent of the transmitted power. So co-channel interference is the function of two parameters R and D, where R is the radius of the cell and D is the distance to the center of the nearest co-channel cell. Okay, so if you look at the diagram you might understood. So these yellow shaded cells are called as the co-channel, which are using the same set of frequencies. Similarly, the cells with the same number are also called as the co-channels that utilizes the same set of frequency. Okay, suppose R is the radius of the cell and D is the distance to the center of the nearest co-channel cell. So D is nothing but a distance between the center of the nearest co-channel cell is called as a D. Okay, and the ratio Q, that is nothing but a co-channel reuse ratio, is called as D by R, where D is a distance, R is a radius. If this R is reduced, then interference is also reduced. So we want to reduce the radius of the cell, that is size of the cell. to minimize the co-channel interference. Okay, this is the example diagram which shows the frequency reusing concept and the co-channels and how the interference will be reduced among these co-channels. As we know that we are following a hexagonal geometry for a cellular architecture where Q is equal to D by R, which is equal to root of 3n. Okay, suppose if you choose this Q value to be small, it provides a higher capacity, that is a larger capacity could be obtained by keeping this Q to be small, but the large value of the Q will improve the transmission quality. Okay, so we always need a better transmission quality as well as a larger capacity. So both the factors are very important. So we have to choose the Q in such a way that it will be a trade-off between these two objectives. Okay. So this table shows a certain number of the co-channel reuse ratio and for some values of n. Okay. For example, see this first row where I is chosen to be 1 and j is also 1, where the cluster size n is to be considered as 3. So for this case, your co-channel reuse ratio Q to be 3. For the second case where I is kept to be 1, where j is increased to 2. Here your cluster size is 7, that is you have a 7 cells. Okay, your co-channel reuse ratio Q is calculated as 4.58. So likewise you can have a number of values based on your design. Suppose let I not be the number of co-channel interfering channels. There are totally I number of co-channel cells are there. Then the another important factor in this interference is the signal to interference ratio, SIR, the ratio of signal to interference, S by I. So which is equal to S by the total number of power, interference power, summation of the power created by all the interfering co-channel cell base stations. Okay. So S is nothing but a desired signal power and interference ratio is summed up all the interference power caused by individual cells in the co-channel cell base stations. And N is considered to be the path loss exponent which ranges between 2 to 4. So the average received power PR is calculated as P0 into D by D0 the whole power minus N. While you write this equation in decibels, we could able to write it as PR, that is received power, measured in dBm, which is equal to P0 in dBm, where this PR is a received power. P0 is considered to be the close-in reference distance, that is the nearest point from your receiver. Okay, so which is called as a P0. So P0 dBm minus 10 in log d by d0. Logarithmic value of d by d0 will give you the received power. Okay. So S by I is calculated by root 3 power n the whole power n by I0, where I0 is the total power. Here we consider only the first layer of interfering cells. Okay, so this is the example taken from AMPS, that's your first generation cellular mobiles, which requires the SIR to be greater than 18 dB. So in this case, N should be at least 6.49, capital N, for a small n 4, and maximum cluster size is 7 for this case. So this is another example of a co-channel interference where we consider the hexagonal geometry with 7 cell cluster with the mobile unit being at the cell boundary. We are considered that our mobile is at the boundary of the cell, and based on this we are calculating the SI ratio for the worst case, and it will be approximated as given in this figure. Next we move on to the adjacent channel interference. So adjacent channel interference is nothing but interference caused due to the adjacent in frequency to the desired signal. That is, nearest frequency bands are interfere with each other. That is called as a adjacent channel interference. This is mainly caused due to the imperfect receiver filters, which allows a nearby frequencies to leak into the passband, and due to this performance may be degraded seriously due to near far effect. Okay, so look at this signal here. This is the filter, improper filter. Because of this extension of the filter beyond the passband, there is certain leakages from the adjacent channels to the required one. So that will create a interference. This adjacent channel interference can be minimized by means of choosing a perfect filtering, or at least a filter which gives a minimum interference, and by means of a proper channel assignment. So this is the another representation of adjacent channel interference. Here you might look at this. This blue line indicates one signal and this red lines are in another signal. While at this area both of them are interfere with each other because of improper filtering. So that could be avoided to get a proper signal quality at the end user. And we keep the frequency separation between each channel in a given signal as large as possible. So a channel separation greater than 6 is needed to bring the adjacent channel interference to the accepted level. So here the problem is called as a near far effect. The other transmitter captures the receiver of the expected subscriber. So instead of the expected subscriber, another transmitter will capture the signal quality. That is called as a near far effect. Also, when a mobile station close to the base station transmit on a channel or close to the one which is being used by the weaker mobile. Okay, so in this case it's bleeded over to the adjacent channel mobile, because when a channel is moving towards the another base station which has very strongest signal, ultimately the channel is, that is the mobile is attracted by the strongest base station, isn't it? So that effect is called as a near far effect. Suppose consider here, this is your base station act as a transmitter. This is your mobile user which is nothing but a receiver, whereas this is the expected base station where this one is the unintended transmitter or unexpected one. But your mobile receives the strongest signal from this unintended transmitter instead of where it has received a weaker signal from the expected transmitter. So in this case the mobile receiver is captured by the unintended, ultimately because it provides a strongest signal, because the mobile user doesn't know who is the intended one. Based on the signal quality, it is attracted towards the unintended. So this effect is called as a near far effect. This is the case 1. The case 2, consider this is the desired mobile transmitter. This is the actual receiver. But the connectivity is by means of a weaker signal, where another transmitter which is nearby to the receiver provide a strongest signal. So ultimately this signal could be received by the receiver instead of the desired one. Okay, this is also another case of a near far effect. So in both the cases, we cannot, first case we cannot able to connect with the required receiver. In the second case, we cannot able to receive from the required transmitter. So in order to minimize this adjacent channel interference, as we discussed, first one is we have to follow the careful filtering. That is a minimum leakage filter or a short transition filter. Second one is we have to use the better channel assignment strategies. Okay, channels in a cell need not to be an adjacent. For channels within a cell, keep frequency separation as large as possible. Also, a secondary level of interference can be reduced by not assigning the adjacent channels to the nearby cells. Okay, for tolerable adjacent channel interference, we either need to increase the frequency separation or to reduce the passband bandwidth. And also we have to control the power for reducing the interference. So ensure each mobile transmit the smallest power necessary to maintain a good quality link on the reverse channel. So forward channel is from the user to the base station. Reverse channel is from base station to the back to the user. In order to have a long battery life and increasing signal to interference ratio and solve the near fault problem. So this is the one of the solution for reducing the interference. So in this video we have discussed a type of interference and how to mitigate them. Thank you.